Well, hello everyone, and thank you for joining us for our presentation, MPC Research Hybrid Post-Tensioning Columns, MPC Project 588. Today's presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which now includes 9 universities in Colorado, Montana, North Dakota, South Dakota, Utah, and Wyoming. Our speaker today is Dr. Chris Panelides. He's been with the Department of Civil and Environmental Engineering at the University of Utah since 1991, where he is currently a professor and associate chair. He received his BE in Civil Engineering from the American University in Beirut in 1980, his Master's of Science from the University of Missouri, Rolla in 1983, and his PhD from the University of Missouri, Rolla in 1987. He was a design structural engineer in 1980 with Darhal Handashah Consultants from 1981 to 82. He was a construction engineer with Odin and Odin Stromaten, SAM. With that, Chris, I'm going to go ahead and turn the presentation over to you to begin your part.
Thank you very much, Chris. Good morning, everyone. As you can see here, I'm from the University of Utah. Nice of you to join this webinar. And before I start, I want to make sure that I acknowledge my co-author, Ijan Dango, who was my PhD student now, and he's graduating with his PhD. And he did the work that you're going to see here, along with some of my other students. In this presentation, as you know, Utah in the last 2 years, now it's a reminder we're living in a seismic area. We had the earthquake in Magna, 5.7, with some actually damage to masonry, mostly buildings, but also some damage, superficial at best, to some of the bridges. But we're aware of the seismic issues here in Utah. So this work is actually in that direction. We're interested in seismic performance of bridges. So in my presentation today, I will make a short introduction to this topic. I will present an experimental test, which included a post-tension bridge bent with a backling restraint brace. Then I will present the analytical study for this test and the efforts that we made to simulate the experiment. And then I will move on to an evaluation of a 3-column bridge bent, which we have carried out on a bridge that I had previously tested, and we modified to follow more or less the experiment that we did in the lab. And I will close with some conclusions. So as you know, accelerated bridge construction is one of the methods that currently is promoted by the US DOT. Utah has taken, I would say, a leading role in this construction method because we have minimal interruption to traffic, higher accuracy in construction, higher level of safety, and improved workability under challenging conditions, especially in urban areas. So this brings me to the introduction of the post-tension bridge bent, which you can see here, which mainly consists of 2 footings, 2 columns, and a cap beam. And this is pretty much the experiment we carried out with the addition of an external energy dissipator, which is the backling restraint brace. So a post-tension bridge bent includes post-tensioning bars or 7-wire strands, like you see here, the 2 lines that follow from the bottom of the footing to the top of the cap beam. These are the post-tensioning bars. These bars may be bonded or unbonded. And of course, the idea is that these bars are providing the self-centering that's required after an earthquake, so that if there is a strong earthquake, the bridge will come actually after the earthquake back to the original position. That's making it serviceable. People can drive over it, especially after an earthquake when they're trying to get to a hospital or some place like that. So it's a very advantageous system. And of course, that makes the bridge resilient, and it has very good results. So in order for this to be the case, though, the post-tensioning bars need to remain elastic at large drift ratios so that they can provide the restoring force. So the drift ratio, very quickly, is actually the ratio of the lateral displacement in the transverse direction, which is known here as delta, divided by the height of the columns up to the middle of the cap beam, and we define this as the drift ratio. Now, in the laboratory, these post-tensioning bars or strands can always be retension or replaced, but of course, in an actual bridge, this would be a challenge. So post-tensioning bars, you can see here an image of a typical post-tensioning bar. This shows pretty much the threaded bar, which is typically 150 KSI strength. And you can see also the collar at the end. And you can see also the duct and the grouted tube. Typically, these bars are grouted, although in our experiment, as I will show, we didn't grout it. And most DOTs want to grout this because of corrosion issues. So you will hear me say the word hybrid. Why is this called a hybrid bridge band? It's hybrid because it's made out of two essential components, the post-tensioning element, which I just described, and typically an energy dissipating element. So what that means is the post-tensioning bars or the strands are providing the recentering, and then the energy dissipating element, in this case the BRV, is providing the hysteretic energy out of the system. So as I mentioned, the post-tensioning bars or the strands should not yield. Otherwise, they cannot generate the restoring force to self-center the bridge band. On the other hand, the residual drift in this hybrid bridge band should be very low during a seismic event. And by residual drift here, we're talking about when the load goes down to zero, then the displacement should come as close as possible to zero. In other words, the delta residual plus or minus should be very close to zero. Now, as far as the external energy dissipators, there are many different types. There are steel bars or plates. There is, we actually did a study on stretch length anchors. And in this particular experiment, we are trying to use a buckling restraint brace. Now, a buckling restraint brace, these were used early on in Japan in the early 80s. Basically what it is, it's a dog bone, a steel dog bone that you can see here, which has a yielding part in the middle and an elastic part at the end. And it's enclosed inside a steel casing, a steel tube. And inside the tube, there is a concrete filler. But between the concrete filler and the steel core, there is an air gap. This air gap allows the core to yield both in tension and compression and display similar performance for many cycles, and by preventing the buckling of the dog bone, the steel core. So you can see here in the force displacement curve under cyclic load, typically after the elastic range, the core will yield in tension, and as it goes into compression, it will yield in compression as well. And after that, it goes back into tension and it keeps doing that. Whereas if we had a typical brace without, let's say, just a steel HSS tube, without any concrete, it would probably after buckling, after compression, it would buckle like this. So the energy dissipated would diminish very quickly, as opposed to the buckling restraint brace, which actually can go on for many, many cycles. Now, it's not exactly ideal, as you see here. Typically in compression, what happens to the BRB, it gains strength. And the body can still absorb a large amount of hysteretic energy during an earthquake through mostly repeated hysteresis loops. Now for design, the strain range and the limit state of the BRB, there is a little hardening that happens in tension and considerable in compression. So there are special factors that take that into account. But the typical range that these BRBs are designed for, mostly in buildings, of course, is a strain of about 2.5% in tension and 2.5% in compression. The 2.5% strain in tension is itself very important and very impressive, but the 2.5% strain in compression is extremely impressive. So it's a very good energy dissipation system. Now, these buckling restraint braces have been used in monolithic bends, mainly for retrofit. So here is an example by Bazais and Dusica, who did an experiment with the buckling diagonal buckling restraint brace, as you can see here. And of course, they observed minimal damage to the reinforced concrete components and achieved high displacement ductility of the retrofit structure and improved overall the seismic base shear capacity. However, the difference between this particular experiment and what we are attempting to do here is this is not a self-centering bridge. In other words, at the end of the test, your bridge may have a permanent residual deformation. Whereas in our test, the implication is that by post-tensioning the column to the cap beam and the footing, that the bridge will come back to its original position. So if we compare then the axle bridge construction against the cast-in-place design method, construction method, we will see that if we compare in terms of structure cost, the cost for the cast-in-place is low, but the ABC with the hybrid will have a little bit higher cost, so it's medium. The duration for cast-in-place is high, whereas the ABC is low. Maintenance cost and duration, it's going to be medium for the cast-in-place, but low for the hybrid. And especially the post-earthquake repair cost and duration will be high for the cast-in-place and low for the ABC. So as an inspiration for this work, we looked at a bridge that actually exists in Utah. It's in a city called Ogden, north of here, Salt Lake City. It's called the Riverdale Bridge Bend. You can see this is normal to the highway I-84 and goes through I-15. It's a bridge with typical bends, and the typical spans are 76 feet here. So here you can see the bend 2, which was the middle bend, and you can see it has 4 two-column bends. And here are some typical details of this bend. It has a 3-foot 6-inch columns, octagonal, and 4-foot pile caps and 4-foot cap beams. These post-tensioning is made with bars again, and these bars are grouted, post-tensioning bars. And of course, we have a shear key here in the footings. So this is the typical section of the column. You can see each column has 6 post-tensioning bars, number 11, and number 4 spirals at 4 inches. There is a rebar in the columns, but cross into the footing or into the capping. So this allows, of course, the column to be reinforced, but the only connection between the cap beam and the footing and the column is through the post-tensioning bars. 4 of these post-tensioning bars end up at the top of the column, like you see here, and 2 additional bars end up at the top of the cap beam, as you see here. So this is the system that we based our design. You can see the cap beam is 4 feet by 4 feet, and of course it's designed to remain elastic. And the same thing is true for the pile caps. So what we decided to build in our lab is something that would fit in our lab, and we tried to emulate at about 40–45% scale a typical bend of the Riverdale Bridge, and the columns, the footings, and the cap beam We try to design these to stay as capacity protected members. And here you can see clearly why this is a hybrid bridge system. Each column here has two bars, two post-tensioning bars in it. And these are unbonded bars as opposed to the actual Riverdale Bridge. And then this is our self-centering system. In addition to a gravity load that I will show you a little bit later, it tries to self-center the bridge. And as far as the energy restraint brace, this brace is attached to the pile cap. I will show you the details, and also to the cap beam. And this is, of course, considered to be a sacrificial member because after an earthquake, we can replace this BRB with a new one if it gets damaged. So the footing details is a 3x6 footing in plan view, 19 inches is the height. Is reinforced to remain elastic mostly. There are some extra details and it's capacity protected. The shear key, you can see the shear key here. In this particular experiment, we were trying to protect the footing from having any damage. So we placed some steel plates and polyurethane plates inside the footing to distribute the compression forces that are very high in this area. Here is the detail of the column. We used number 5 spiral at 3 inches, 12 number 5 post-tensioning bars, grade 150 KSI. Here you can see we used some footing and in the cap beam, and we had to make sure we were meeting the clearance requirements and the tolerance requirements. The column also had steel collars, 16 inches at the bottom, 8 inches at the top. At the top, there was no, as I'll show you shortly, there was no shear key at the top. It was just a flush. But you can see in here as well, in the cap beam, we have receptors. We have the PVC pipe so that the post-tensioning bars can go through all the way from the bottom of the footing to the top of the cap beam. The cap beam is 1'7" by 1'10" and is very heavily reinforced. As you can see here, again, it's capacity protected. And you can see the extra reinforcement around the area where the post-tensioning bars are going through. The span between the two columns, you can see center to center is 10 feet. So as you can see in this graph, one key requirement is what post-tensioning stress you initially should stress the post-tensioning bars. So in order to do that, you have to look at what is your target drift. In this case, it was something between 2 and 3%. And then you can calculate, of course, what is the rotation of the column. And based on this and the distance of the post-tensioning bars, as I mentioned, 2 per column, you can find what the elongation of these post-tensioning bars is. So as you increase delta, or the drift ratio, which is delta over H, as I described earlier, you can see that for different initial post-tensioning stresses, these stresses are going to increase as the lateral drift increases. And of course, one of the key elements here is, depending on what your target drift is, you can find out whether or not at that target drift, the post-tensioning bars are going to yield or not. So obviously, if we started out with 80 KSI, we actually would have yielded the post-tensioning bars at 4.5% drift ratio. So in our case, we started with a relatively low initial post-tensioning stress, about 50% of the yield, which is roughly 60 KSI. The second, of course, requirement here is, how do you design the buckling restraint brace for the hybrid post-tensioning bend? And what this means is, buckling restraint brace, as I mentioned earlier, is characterized by strain capacity, but also by strength. So here on the right-hand side, you can see a prediction of a pushover curve of the post-tensioning bridge bend without the BRB, which is the straight black line here. And then what you are seeing here is the pushover curve for different tensile capacity BRBs, like 20 KSI, 20 kip, 40 kip, 60 kip, 80 kip. And obviously, in all of these cases, the initial post-tensioning force in the tendons of the PT bars was 50% of the yield. So you can see that if you use a very high strength BRB, like the 80 kips, you have the capacity to go very high lateral force, like 180 kips. But then once the BRB fractures, then it will drop back down to the pre-stressing bend without the BRB. So you have to be careful here how you design it. And we were trying to develop some criteria. In the end, you don't want it to be very strong, but also you want it to be strong enough so it does some benefit. So here on this middle curve, you can see we have the red line here is the pushover curve of the post-tensioning bend without the BRB. The blue line is the force deformation, displacement deformation of the BRB itself. And the green line is the composite, in other words, the hybrid bend with the post-tensioning and the BRB. So based on these curves, we developed some criteria which we're proposing here. One of the criteria is that the yield displacement of the BRB has to be small enough to start working before the post-tension columns start to work. So in this case, we decided to say that the yield displacement of the BRB, this line here, should be no more than half of the displacement of the post-tensioning at yield. So if this is the displacement of the bend when the post-tensioning bars yield, we want the BRB to yield at least half of that, okay? Less than half of that. So that means the BRB will start yielding first before we even get close to yielding the post-tensioning bars. Similarly, the force in the BRB, which is this one here, the combined hybrid bend, must be less than the yielding of the BRB, of the post-tensioning columns themselves. So this is the yielding point, and we want the composite to be less than that. And the overall strength, we want the strength, which is this point here, to be less than 1.5 of the post-tensioning bend itself. Otherwise, the system becomes too strong and it will overwhelm the other components. So these were the three rules that we came up with. And then we had to design the connections. So in the connections, a very important part is that these anchors, we started out as adhesive, but it wasn't sufficient. So we use all threaded bars for the whole thickness of the footing. And then, of course, we had to design the gusset plates for accepting the BRB. And in addition, we had to design some vertical stiffeners. These vertical stiffeners are necessary, so when the column is rocking, of course, it will not touch. So we had a gap here at the bottom of 3 inches, and we had additional stiffeners to prevent buckling of the gusset plates. Up here at the top, at the cap beam, we have bolts, all threaded bars that go through the cap beam. And again, we have the vertical stiffener, which is necessary to prevent buckling of the gusset plates. We also had 2 additional stiffeners to make sure that the gusset plates do not buckle. And here we had a gap of 2 1/8 inches. Both of these gaps were more than sufficient to ensure that when the columns were rocking, they would not touch the vertical stiffeners. So how do we guarantee recentering then of the hybrid post-tension BRB bend? So there are some previous works that were done mainly in New Zealand and also here in the US, where people are thinking of some requirements of how do you self-center a bridge bend. And basically, I'll go to this slide first. The idea is that the total moment at the bottom compared to the dissipating moment should be less than 50%. This ratio needs to be less than 50% so you can self-center. And also the ratio of the moment caused by post-tensioning and the axial load divided by the dissipating moment should be more than 1. So how do we define these quantities? So the post-tensioning, if we look over here, we can see that the BRB has a working point which coincides roughly with half the thickness of the cap beam and half the thickness of the footing. And this is the center line of the two tendons. You can see in each column we have two tendons. So if we sum moments about this point here, O, we can see that the self-centering moment is the force due to the post-tensioning bars times the span. The span here is called L. And then we have also an additional axial load, which comes from, of course, gravity. In our case, in the experiment, we use some rods with a self-reacting beam to achieve this. So it's this force due to gravity times span over 2. And then what is the dissipating? Of course, the dissipating moment comes from the BRB, mainly. It's the force in the BRB, which is either in tension or in compression, times the cosine of this angle gamma. Gamma is the angle of the BRB with the horizontal. And then times the moment arm, in each case, which is the height of the column, plus half the height of the beam and half the height of the footing. Now, when we say the force in the BRB, as I mentioned, we have to account for hardening effects, both due to compression and tension. And these are the numbers that were significant in our test. The span 10 feet, as I mentioned, the height 84 inches, and the height of the beam and the footing 19 inches, and gamma was 41 degrees. So based on that, the dissipating moment, which is due to the BRB, divided by the total moment, which is everything else in the system, needs to be less than half. In our case, this ratio was roughly about 1/4, which is less than half, so we were sure that we were not overburdening the system with the energy dissipation. And then the other here is the lambda. The lambda comes from some criteria developed in New Zealand. Here is the post-tensioning moment. Here's the axial moment. And the denominator, it's some hardening factor times the moment due to the BRB, which is the energy dissipating system. And you can see when the post-tensioning moment and the moment due to the gravity load is larger than basically 1, then of course that means it will self-center. And here in our case, it was much more than 1. It was about 2.9. So we expected that we will have self-centering. So here in this image, you can see how we did the test. And you can see how we applied the axial load. We had a system whereby the actuator was pushing up on a beam, like you can see roughly here. And then these two rods, number 11 axial rods, one on each side, were reacting to the floor. But in between, we had some rollers so that we would make sure when the bend was drifting to the right or to the left, we actually tried to maintain these rods as vertical as possible so the axial load would not be increased. So here you can see the picture of the experiment as it was carried out. And of course, this hydraulic actuator induces the positive and push and pull movement of the bend. And the force inside the bend is transferred to these rods, threaded rods, with 2 channels, one on either side of the capping. We monitor everything. We instrumented the BRB to measure its elongation. We also had a load cell on each one of the post-tensioning bars, as you can see here, to measure the post-tensioning. Again, the reinforcement, the mild steel, did not penetrate the footing or the capping. It was self-contained, as you can see here. We had strain gauges, of course, on the hoop bars and also the spirals and also on the vertical bars. Here you can see clearly the gap between the vertical stiffener of the gusset and the column. Also some detail of how we measure the rotation of the column. And here you can see the two additional stiffeners that are helping protect the gusset plate against buckling. So the loading protocol was 2 cycles at increasing drift ratio from 0 to practically 6% drift. And you can see the number of cycles is around 22. So this curve shows the hysteretic response, the lateral force versus drift ratio of this hybrid system. We did not observe any cracking along the length of the column due to placement of the steel collar. The BRB yielded at about 1.5% drift ratio, and the steel core fracture about 5% drift ratio. And after the BRB steel core fracture, the 2 post-tensioning bars yielded at about the 6% drift ratio, you can see here. And the longitudinal steel column bars also yielded around that 6%. The columns had a very good performance. Here you can see the rotation in radians versus the drift ratio, both at the top and the bottom. Very adequate rotation, although not perfectly symmetric. As far as the longitudinal bars, we yielded, as I mentioned, on the east face of the east column at the bottom, but that didn't happen until 6%. And on the west face, we actually didn't have too much, about 50% of yield at 6% drift ratio. As far as the hoop strain, it was very small. We expected that. And as far as the strain in the steel collar, we can see that it's roughly, again, about 50% of yield. The post-tensioning forces, you can see here that we didn't yield until we got very late in the game at about 6% drift ratio, which is very good news. And you can see the condition of the bars, the 2 bars in the east column and the 2 bars in the west column. Actually, the west column came close to yielding, but never yielded. Only the east column yielded. There is some, as you can see, variation with the application of additional drift. You may start it out as 50 kips, but of course, as the columns drift, the bars elongate, and they kind of, as you can see barely here, they touch perhaps the interfaces and they start gaining strength. So from 50, we went up to 120. In this case, more or less below 100. So then the question is this good performance? Of course, it's good for performance, but then the question is, how much residual drift do you get? Well, here in this graph, we have the horizontal axis is the drift ratio. As I said, 6% was the maximum we reached. And the yellow is the maximum lateral displacement. And in gray is actually the residual. So we can see at each drift ratio what the residual is. So for example, at 3%, the residual is less than 1%. And of course, at 6%, or let's say 5%, when the BRB was still there, we had a residual roughly 2%. And then at 6%, of course, once the BRB fractured, we went back down to 1%. So this is sort of like an index of how well you're doing. And 100% or 1 is perfect recentering. And of course, here we see we're around the 0.8 or less. The BRB itself, we measure its axial deformation in inches, is the vertical axis for different drift ratios. And on this side, you can see perhaps more importantly, the strain. And you can see that the strain we achieved was very high, up to 28 times the yield strain before it fractured. A little bit more than 28, actually about 30 times. Just as a reference, in building design, the design for buildings, the target is 10 to 15 times the yield. That's the design strain in a BRB. Here you can see the condition of the BRB ends at different drift ratio. This is where it yielded. As you can see here, the line is red, it's broken. And here is 32 times the yield at 5% ratio, right about where it fractured. And here is, again, you can see how much it elongated. And this is 6%, where, of course, it fractured and the strain now is 0. This is the stiffness of the bend, the hybrid bend. You can see we start pretty high, but then as drift increases, it drops significantly, the secant stiffness. Here is the energy dissipation. You can see it's very satisfactory. This is the area under the hysteresis loops. And you can see here it's very good until the BRB fractures, in which case it will drop. And of course, from that, we can define an equivalent damping ratio. And here you can see up to the point where it fractured is about 15%. So we can say that the hybrid bridge bend with post-tension columns and the BRB had an excellent performance. It added strength, stiffness, energy dissipation ability, and damping through yielding of the core until fracture. And residual drift at very high drift, about 5%, was 2.3, but of course at lower drift ratio was 3%, it was only 1%. And of course, what this BRB helped, it delayed yielding of the post-tensioning bars. So in the second part of this presentation, I want to talk a little bit about the computational model. We use OpenSys, open source software for finite element analysis. It's very versatile and it's more used for research than design, but it does create a reliable model for simulating the post-tension bridge bend we tested. So of course, our goal is to also simplify these models. And I have a student now who is currently working on this. And to simulate, of course, the rocking is challenging. And this assign an appropriate stress-strain relationship. So we start out with the concrete. We have a core and the cover. We have mild steel, and then we have the steel collar. And in addition here, we try to simulate the post-tensioning bars. Most people use monotonic. We try to do a cyclic model, and you can see the information here. As far as the BRB, we modeled it using uniaxial material, and we have done some experiments in the lab. These are uniaxial tests, which actually helped us develop better the elongation characteristics as well as the energy dissipation. So this shows you the model layout, more or less, of this test, which uses elastic beam column elements here for the gaskets. We use a co-rotational truss element for the BRB and for the axial rods and for the post-tensioning rods. We use the elastic beam column element for the cap beam, and you can see a nonlinear beam column element for the columns and different sections of the column. And there are many assumptions here. We assume the columns the footings are fixed, the cap beam is rigid, the frictional forces are ignored, and the post-tensioning bars behave as straight, and we ignore buckling of the post-tensioning bars. The P-delta effects and the P-delta moments are counterbalanced, and of course we didn't model torsional or out-of-plane deformations of the gasket and the BRB. So we had a kind of a flow chart here that defines the properties, the rocking parameters, the horizontal springs and the interfaces. And we tried to match the hysteretic response to stay under 15%. We tried to match the yielding cycle of the BRB and the fracture cycle of the BRB. And the response of the post-tensioning bars, the force in the post-tensioning, we measured with the load cells to again stay within 15%. And one that was a little bit extra difficult was since we used this polyurethane, we had to do some testing of the polyurethane material for the rocking and the gap element that was created. And we tried to model that with another student, Duc Tran. To some extent, it was successful. And here you can see the experiment in blue line, the hysteresis force, and the open seas model in red, which actually is a pretty satisfactory match. We modeled the energy and the stiffness, again, rather well. And here is modeling the post-tension force in the BRB, in the post-tensioning bars. And you can see that we can model it rather correctly, even though not perfectly. So here is the BRB force comparison and the accumulated damage, and you can see we're actually doing pretty well. So this model captured the stiffness, the strength, the energy of the hybrid bend. The post-tensioning bars were predicted well, and the BRB parameters were sufficient in predicting the response. The BRB axial force is one thing that's an advantage here by the numerical model, which is otherwise difficult to be known in the experiment. And of course, fatigue loss has to be modeled correctly. So why did we do this? Because we wanted to actually model an actual 3-column bridge bend. This is one that I tested about 22 years ago on I-15, which is demolished now, but here you can see the dimensions. And of course, we came up with different details, as you can see here, to make it modern. And of course, we had to make the columns. This was a cast-in-place bridge, and here we tried to simulate rocking, again, at the two interfaces. And we use 4 number 10 post-tensioning bars. And of course, we use the same dimensions that we had done before. This was 3 foot by 3 foot column. And all the other dimensions are very similar to the existing I-15 South Temple bridge bend. And we used, of course, here type of a chevron arrangement with 2 BRBs, as you can see here. All 3 columns are post-tension. This is, of course, an ideal situation. And in this case, we also modeled the cap beam and the pile caps and the piles. So it's an ideal situation. Here you can see the model that was developed by another student, Andrew Wu. And you can see this is to model the grate beam and the pile cap frictional spring. And the agreement with the model is pretty good. And we had to make some evaluation. Site class D was assumed. We studied both far field and near field or pulse type ground motions, and based our evaluation on the hazards model with 4 damage states: slight damage, moderate, extensive, and collapse, based on the drift ratio. So an intensity measure was taken as the spectral acceleration of the first period. Here is a typical list of some 14 ground motions from near field earthquakes. These are actual records. And we try to, of course, come up with a scale response for both the design basis and maximum credible earthquake. Design basis is 10% probability of exceedance in 50 years. Maximum considered is 2% probability of exceedance in 50 years. So after we did that, we did some analysis both for near field, nonlinear dynamic analysis, and far field. And you can see the response here, base shear versus drift. And here you can see the axial force in the BRB versus drift. And of course, most of these earthquakes will not go to 6%. Most of them will go to 2% drift ratio. And we tried stronger earthquakes in both near field and far field. And we didn't have a lot of maximum drift, as I said, about 1.6. And maximum PT bar force is 66 to 67 of the yield. So we tried to do a probability of failure here, both for near field and far field, for both for the design and also the maximum credible earthquake. So the results were actually satisfactory. We did yield the BRB, of course. And I think this analysis showed that we can actually use this type of analysis, which is very high-end, to predict what will happen, and the hybrid bend for the actual bridge seems to be acceptable for the earthquakes we try to do, the maximum that we can see here in our area. So these fragility curves give an idea that how much we're going to be damaged, but I think the damage was actually acceptable in the event of a maximum credible earthquake level even, both for near field and far field motion. So there is the post-tensioning force stayed under yield, well under the yield, and that we had pretty minimal response, both near field and far field earthquakes. So I want to close it because I see there are some questions here. Give some time for questions. Both the Brent and the post-tension columns and the BRB, they had a pretty good performance with stable and symmetric hysteresis. The BRB added significant strength and stiffness to this hybrid bridge bend by yielding of the core and fracturing it eventually. It prevented yielding of the PT bars up to 5% drift ratio, which is pretty high, and increased the energy dissipation very significantly. So the equivalent damping increased after yielding of the BRB and reached about 15% of critical. The computational study with open seas used steel form material to predict the post-tensioning force and the cyclic forces in the bars, and the three-column bridge bend showed very good seismic response with rocking. Now, in the bend with BRB, when the PT bar yields, the residual drift is high, but up to 3% drift, it was still under 1%. Many people consider 1% as a good recentering drift. So we would say that we could operate immediately after an earthquake. By adding BRBs, not only we reduce the seismic demand on the post-tensioning bars, but of course we prevent damage to other components. And so hopefully the bridge will stay functional after large earthquakes. So I want to acknowledge Mark Bryan, laboratory manager, and many students who helped, as you can see here. And of course, the Mountain Plains Consortium and the Project 588. Core Brace for donating the BRB, BASF for donating the polyurethane material, and of course, the Department of Civil Environmental Engineering at the University of Utah. These are the references that we used in our work, a significant number here. And I just want to thank you for listening to me. And I think I have some questions in the chat. Chris, can you read me the questions?
I don't have any on my end.
Oh, you don't?
Hold on, there's one that just popped in. Okay.
Oh, yeah, I can see them now.
Okay.
So, okay, why such a shallow spacing for the spiral ties? So this is an experiment done in the laboratory, and we want to make sure, of course, that we don't have any unexpected results with our columns. And to be fair, we had asked for number 4, actually, spirals, but the delivery came as number 5, so we took it. We knew it was going to be, yeah. So, of course, in the field, you would have a different spacing. So is the BRB most effective when gamma can be close to 45 degrees? Yeah, I think, of course, that's true. But they have used it anywhere from 30 to 60 degrees and with no problems, even, I think, even higher than that. So they're very good at using BRBs at different angles. So these are the questions that I see. I don't know if somebody else has a question.
That's all I've gotten on my end too. If anybody does have any questions, please, again, either put them in the chat or unmute yourself and ask your question directly. And in the meantime, as usual, Dr. Panelides, wonderful, wonderful presentation. Thank you for sharing your experience and the research that you guys have been conducting. Extremely valuable. So today's slides will be made available to you. They'll be located online. And Dr. Panelides, are the slides going to be available right away and then the final paper will be available later? Or do you want to make some adjustments to the presentation yet?
I still have, as I mentioned, Chris, we're doing the final report right now.
Okay.
For the MPC, and once we hear back from the MPC and our report is finalized, I want to synchronize
Okay.
slides. So
Okay,
yeah, you can make available the presentation. We'll get back to you with the slides a little bit later.
Okay, so the recording will be made available, the slides and the final paper will be available at a later date. So just kind of keep an eye on the website where the research is located. All right, well, if there are no additional questions or if there's nothing anybody would like clarified, thank you guys for attending our TLN event in the middle of August. So this is unusual for us, but we want to accommodate our MPC researchers wherever we possibly can. So thank you guys for your time and attention today. We certainly appreciate it. Chris, thank you again for sharing this information. We certainly, again, appreciate your time and your expertise and what you're sharing with this research. It's very valuable. If anybody has any comments or questions, feel free to reach out to us via email. We'll be sure to forward those on if we need to. But again, keep an eye on the TLN website at translearning.org for upcoming learning opportunities. We'll be rolling out our next round of presentations here, hopefully by the end of September. They'll be posted on our website so you can see what is upcoming. With that being said, thank you everybody again for your time and attention. Have a fantastic week. Be safe and don't forget to be awesome. Take care, everyone.